तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we continue our discussion on deterministic inventory models. We have already defined inventory control and have introduced the various costs associated with inventory systems. These are cost of the product, ordering cost, carrying cost, and shortage cost. We have also seen that we will be addressing deterministic inventory models in this lecture, and that the most important decision in inventory problems is how much to order. Now, the solution to this is called the order quantity, which is denoted by the capital letter Q. The costs have been discussed in more detail. We have seen some aspects of the cost of the product as well as the ordering cost C0. Now, let us look at the various aspects of the carrying cost, which is CC. Now, the carrying cost is represented as rupees per unit per year. The various costs that contribute to carrying the items are: 1. Cost of capital. Now, in order to buy these items, we need to borrow money, and there is a certain amount of money that is spent as interest on the money borrowed. So, that is reflected in the cost of capital. Cost of people. The items that have to be carried are stored in warehouses, and we require people to handle and to control these warehouses. Cost of space. Now, we require space to carry these items, and we pay rent and we incur other costs associated with space. There is also the cost of power, which is needed to maintain the warehouse. In addition, we might require some very special facilities such as air conditioning, chillers, and dust free environment for certain items, and therefore the cost of carrying such items increases. In addition to all these, there is the cost of pilferage, where it is likely that a small portion though of the items may be stolen, and there is an associated cost of pilferage, and there could be cost of obsolescence. Items are bought in large volumes and stored, and there could be occasions where by the time the item is taken to use, the item would have become obsolete and therefore would become useless. So, these are the various costs that contribute to the carrying cost or the holding cost, represented in rupees per unit per year or money per unit per year. Sometimes when the cost of capital dominates the rest of the cost, that is the first cost, which is the interest paid on the money borrowed, dominates the rest of the cost, the carrying cost is represented as CC equals I into C, where I is the interest rate and C is the unit price. Now, C, the unit price, is represented in rupees or money value, and I, the interest rate, is represented as percentage per year. So, the product will be rupees per unit per year. The last of the costs that we will be looking at is called the shortage cost, CS, C subscript S, and is also represented in rupees per unit per year. In this lecture, when we say shortage, we mean backordering, indicating that any unfulfilled demand is to be met subsequently. The necessary costs that contribute to shortage are loss of customer goodwill, cost of losing a customer, and loss of profit associated with not delivering the product. So, when there is a shortage or when a particular product is not delivered in time, the first thing the organization loses is the loss of profit associated with not delivering the product. In addition, there could be loss of goodwill. The customer may not like the organization if the organization continues to deliver late, and then over a period of time the organization may end up losing the customer. So these are the important components which contribute to CS, cost of shortage. Now the components of the shortage costs are very difficult to measure. They are not as easy to measure as the other costs. Usually shortage cost is given a very large value. We normally assume a large value for shortage cost to minimize the occurrence of shortage in the planning stage of the inventory. Among these three, loss of profit associated with not delivering the product is easily measurable, while loss of customer goodwill or the cost of losing a customer cannot be measured that easily. So CS is usually not a measured quantity, but it is a quantity assumed to be very large so that shortages are minimized during the planning stage. Now let us consider the first model that we are going to see in inventory. In this model we assume that there is a continuous demand and there is an instantaneous replenishment. Now the annual demand is given by D per year. The ordering cost is rupees C0 per order. Carrying cost or holding cost is rupees CC per unit per year. The order quantity is given by capital Q. Now when we say the demand is continuous, we make an assumption that if the annual demand is D per year, then the monthly demand is D by 12, and the daily demand, assuming 365 days, would be D by 365, and so on. The graph here shows the inventory versus time for the item that is chosen. This is actually this is the graph of inventory versus time. Now we assume that an order quantity Q has an order for quantity Q has been placed, and because of instantaneous replenishment we assume that the order has come instantly. Because of instantaneous replenishment, we will assume that we will place the order when the stock on hand becomes 0. So we assume that the order has just arrived and the stock position is capital Q, which is this position. And because of continuous demand is there at every moment of time, the stock position or the inventory position reduces in a linear fashion and it reaches 0 here. Now this is the cycle. The cycle is the time taken from the inventory to reach 0 from Q. Now this is called one cycle, and at the end of that cycle an order is placed for the same quantity Q and it is instantaneously replenished. So the stock position goes up from here to this position, and then the cycle repeats and so on, which is shown in this. The average inventory is also shown here. Now the question is, out of these four, what this order quantity Q is the variable and the other three parameters, namely annual demand, order cost and carrying cost, are known. So the decision is what is the value of Q which minimizes the total cost. Now the two costs that we will consider in these are the ordering cost and the carrying cost. The total annual ordering cost and the annual carrying cost we will consider. Now if the annual demand is D and the ordering quantity is Q, which means every time we place an order we order for Q items, the total number of orders per year is D by Q. The annual order cost will be D by Q into C0 or D C0 by Q, because there are D by Q orders and every time we place an order we incur an order cost C0. Now the average inventory in the system is Q by 2. Now this is seen from this figure. We can compute the average inventory in more than one way. An easy way to do is to average inventory is actually the total inventory is the area under the curve divided by the period would give the average inventory. Now area under this triangle in a cycle is half into base into height, half into T, which is the cycle, into Q divided by T will give us Q by 2. We can also look at it as if the cycle begins with the quantity q, ends with the quantity 0. So, average inventory in a system like this will be beginning inventory plus ending inventory by 2, which is q plus 0 by 2, which is q by 2. So, the average inventory in the system is q by 2. Average inventory carrying cost will be q by 2 into Cc. Cc we have already seen in rupees per unit per year as the cost of holding one item per year. So, total inventory carrying cost is QCC by 2. So, total cost annual, sum of the total ordering cost plus carrying cost will be DC0 by Q plus QCC by 2. Now, we want to find out the value of Q. Q is the only variable in this total cost expression. We want to find out the value of Q that minimizes the total cost. Now, that value of Q is obtained by setting the first derivative equal to 0 and solving. We would get dC0 by q square, this 1 by q will give us minus 1 by q square. So, minus dC0 by q square, QCC by 2 will give us Cc by 2 equal to 0, from which q star, the best value of q is root of 2 dC0 by Cc. This is called the optimum order quantity or the economic order quantity. Q star is given by root of 2 into d into C0 by Cc, square root of 2 times demand into ordering cost by carrying cost. And when we substitute the value of q star in the total cost expression, we get the minimum total cost as root of 2 into d into C0 into Cc. So, we have now solved the first model to find out the value of the economic order quantity. Given the demand, the order cost and the carrying cost, we will be able to find out the economic order quantity and the minimum cost associated with the economic order quantity. Now, let us illustrate all these using an example. Now, let us assume that D is 10,000 per year, the item has an annual demand of 10,000 per year, order cost is rupees 300 per order, carrying cost is rupees 4 per unit per year. From the equation q star is equal to root of 2 into d into C0 by Cc, which we derived here, we substitute to get 2 into 10,000 into 300 by 4 would give us 1224.75 as the economic order quantity. So, for this example, every time we place an order, we would be ordering 1224.75 items. But before we do this, we need to go back here and look at q star equal to root of 2 into d into C0 by Cc, which we derived by setting the first derivative of this expression to 0. And we also need to actually verify that this economic order quantity gives us a minimum total cost. Now, that has to be done by setting the second derivative to 0 or evaluating the second derivative at the point q star equal to root of 2 d C0 by Cc. When we find out the second derivative for this, we realize that the second derivative is positive, indicating that it is a minimum. So, q star equal to root of 2 d C0 by Cc gives us a minimum value of the total cost. Now, when we compute q star equal to 1224.75, Tc star, the minimum value of the total cost is root of 2 d C0 Cc, which we have seen here, gives us 2 into 10,000 into 300 into 4 square root of this expression gives us rupees 4,898.98. Now, what are the other things that we need to look at from this example? 1. The total cost that we have computed here does not include the cost of the item. In fact, in this example, we have not even defined C, which is the unit price of the item. So, the total cost, the economic order quantity and the total cost do not include or consider the cost of the item. This is because we are looking at an annual cost, and the total cost of the items will be D into C, which is a constant and does not depend on Q. So, Q will not have C in any of the equations. Now, q star is called the economic order quantity, called EOQ for short. So, very commonly used term EEOQ to represent the economic order quantity or Q star. The number of orders per year for this example would be N is equal to D by Q. Annual demand is 10,000, order quantity is 1224.75. So, we will be having 8.17 orders per year. Now, the number of orders per year need not be an integer, it can be a fraction. This would simply mean that we would be placing an order every 365 divided by 8.17, roughly every 46 days we will be placing an order if we assume that a year consists of 365 working days. Now, what happens, how sensitive is the economic order quantity, or how sensitive is the cost with respect to the economic order quantity? Suppose we want to round off the economic order quantity to a value 1500. Suppose we assume that the item is available only in say packets of 500 or multiples of 500, and we decide to round it off to 1500, which means we have roughly increased the order quantity by about 15%. If we do that and round it off to 1500 and go back and substitute, total cost is D C naught by Q plus Q C C by 2, and we substitute 1500 here, then our total cost becomes 5000. When we substituted 1224.75, the total cost was 4898.98, but when we substitute 1500, the cost becomes 5000, which is approximately less than a 2% increase from the 0.2% increase from the optimum cost. Now, this is because the total cost curve is very flat near the optimum, and therefore gives the decision maker the flexibility to suitably define the actual order quantity, which could be near the optimum or the economic order quantity. Now, this is shown in this figure. Now, the order cost curve is a D by Q into C naught curve. So, it is a rectangular hyperbola which moves like this. The carrying cost curve is Q by 2 into CC, which is a straight line, it is a linear curve, and the total cost is a sum of this D by Q C naught plus Q by 2 CC, and we get a curve which is like this, and it is very flat near the optimum. This is the optimum Q star, it is very flat. At the optimum we will also find that the total order cost is equal to the total carrying cost, and the total cost is 2 times the order cost or carrying cost. It is very flat near the optimum. So, even if we increase Q by a certain quantity or decrease Q by a certain quantity, we realize that the total cost actually does not increase very significantly. We also assumed in this model that there is instantaneous replenishment. For example, we place an order here, instantly the quantity becomes Q. So, there is an instantaneous replenishment. Therefore, we wait for the inventory level to reach 0, and then we place an order so that the inventory rises to Q. Now, there is something called the lead time, which is the time taken between placing an order and getting the item. Because of instantaneous replenishment, the lead time is 0 in this example. But if there is a lead time, then the time to place an order given by reorder level, or the stock position at which the order is placed, called reorder level, will be equal to the product of the lead time and the daily demand. In this deterministic model, the lead time into daily demand would give the reorder level or the stock position at which an order is to be placed. So, when the stock position reaches the reorder level, the order for Q star is placed. Now, let us look at the second model, which is an extension of the first model, considering backordering. In this model, we allow a backorder of S units every cycle, and as soon as the order quantity Q arrives, we issue the backordered quantity. You can see this in this figure. Now, we start with a certain quantity which is IM, we will see that later, and we start consuming it. Now, here the stock position is 0, but here we do not place an order. Here also we assume instantaneous replenishment. We do not place an order, we allow a back order to build up to a quantity S, then we place an order for q items. So instantly we get the q, but the moment we get this q, the back order is fulfilled. So S out of the q is fulfilled, and q minus S is the inventory position here, which is given by IM or maximum inventory. The subscript M indicates maximum inventory. So IM represents maximum inventory, which is q minus S. And then we consume from this IM till we reach 0. Again we allow back order up to a quantity S, and then once again place an order for q star, and so on. Now in this case there are two cycles. One, there is something called a cycle is divided into two parts. One is the T1 part and the other is the T2 part. The T1 part is the portion of the cycle where we hold inventory, and T2 is the portion of the cycle where we have back ordering. So we use the same parameters, but we need an additional cost which is called CS, which is the shortage cost, but it represents the cost of back ordering. We have already defined CS in rupees per unit per year. Now we have two variables in this. Q, the order quantity, is a variable, and S, which is the quantity that is back ordered, S is also another variable. The maximum inventory held in this example is IM, which is q minus S. Now this becomes a dependent variable. Q and S are the independent variables, and the two cycles T1 and T2 also depend on Q and S. So annual demand is D, order cost is C naught, carrying cost is CC, shortage cost or back order cost is CS, order quantity Q and quantity that is back ordered S are the variables, and the maximum inventory IM depends on Q minus S. These are the various parameters that we will be considering in this model. Now there are three costs that we have. There is an ordering cost, there is a carrying cost, there is a shortage cost. So we compute all the three costs. Number of orders per year is D by Q, as we have seen before. Annual order cost will be D by Q into C naught or D C naught by Q. Now average inventory in the system. Now in order to calculate this, we need to look at this. Now if we look at a cycle, the total inventory that we have in a cycle is the area of the triangle, half into base into height, which is half into T1 into IM. So the average inventory, now there is a total inventory of half into IM into T1, which is held for a time period T1, and there is a time period T2 where there is back order, which means there is a zero inventory. So we carry a total inventory of half into IM into T1, but we carry it for a period T1 plus T2. So the average inventory will be IM by 2 into T1 by T1 plus T2. We look at this. Now average inventory is IM by 2, so we will have actually IM by 2 into T1 by T1 plus T2. That is the average inventory, and CC is the cost of carrying this inventory. So annual inventory cost will be IM by 2 into CC into T1 by T1 plus T2. Similarly, if we look at the second part of the cycle, that is the back order part. So total quantity shortage or back ordered is area of this triangle, which is half into T2 into S. So this quantity is for the entire period T1 plus T2. So average quantity short will be half into S into T2 divided by T1 plus T2, which is shown here, S by 2 into T2 into T1 plus T2. This multiplied by the shortage cost CS would give us a total annual shortage or back order cost of S into CS by 2 into T2 by T1 plus T2. Now we have to optimize this function, but then we have only two variables, that is Q and S. So we have to write IM as well as all these T1, T2 quantities in terms of Q and S. So we go back to this figure and then we observe bisimilar triangles. Now this is T1, this is T2. Now this portion is IM, this portion is S. So, from similar triangles, and this total portion is Q, this is also Q. So, T1 by T1 plus T2 will be Im divided by Q, and T2 by T1 plus T2 is S divided by Q, and Im is written as Q minus S. So, T1 by T1 plus T2 will become Q minus S by Q, and T2 by T1 plus T2 will become S by Q. So, we go back and substitute here. T1 by T1 plus T2 is Q minus S by Q, and T2 by T1 plus T2 is S by Q. So, we go back and substitute to get total annual cost Tc, d by q C naught remains as it is. Now, this becomes q minus S the whole square into Cc by 2q, because this will become Im by q, which is again q minus S by q. So, there is already a q minus S. So, q minus S square into Cc by 2q, and this will become again an S by q. There is already an S there. So, S square Cs by 2q. So, now we have written the total cost expression in terms of the problem parameters as well as the two variables q and S that we have. Now, we have to find out the values, the optimum values of q and S. Now, the values of q and S that minimize the total cost are obtained by setting the first partial derivative of this function with respect to q and S to 0. Now, partially differentiating with respect to S and setting it to 0, we get S is equal to QCc by Cc plus Cs. We have not shown the intermediate steps in the derivation, we have just shown the final result here. So, you can derive this and verify this result. So, S is equal to QCc by Cc plus Cs. This is obtained by partially differentiating this with respect to S and setting it to 0. Now, we have to partially differentiate this with respect to q, and all the three terms involve q. So, it is a slightly involved partial differentiation, and we have to do that, and then in the first derivative with respect to q, we have to go back and substitute for S equal to QCc by Cc plus Cs, and then when we simplify this, we get this expression q star is equal to root of 2d C naught into Cc plus Cs by Cc Cs, or root of 2d C naught by Cc into Cc plus Cs by Cs. So, this is the optimum or economic order quantity in the case that includes backordering. Once again, we go back and we can show that the second derivative is positive at the optimum values. Normally, that is not done, because even in the earlier model, when we know that the second derivative is positive indicating minimum, the same thing continues in all inventory problems. So, it is not customary every time to show that the second derivative is positive. So, we can leave it at that and assume that first derivative indicates the minimum. Now, we illustrate this through an example. We use the same data as in example 1, the same data which is 10,300 and rupees 4, and we include an additional CS shortage cost as rupees 25 per unit per year. Now, when we substitute, q star is equal to root of 2d C naught by Cc into Cc plus Cs by Cs. We substitute here to get 1319.09. S star, which is the best value of the quantity back ordered, is given by QCc by Cc plus Cs on substitution gives us 181.9435. Now, let us go back and compare the results that we had in example 1. Example 1 is similar to example 2 in the sense that the parameters d, C naught and Cc are the same. The additional consideration in example 2 is the build up of the back order. So, if we go back and compare, in the first model, the order quantity is 1224.75, the minimum cost is 4898.98. Total order quantity is 1224.75, which was the maximum inventory that was held in the system. Now in this example, the maximum inventory that we have is Q minus S, which is 1319.09 minus 181.94, which is 1137.147. So when we build a back order into the system, our order quantity increases, but the maximum inventory reduces because of the back ordered quantity, which is 181.94. Number of orders per year will come down. It was 8.17 in the previous case because the order quantity has increased. Each cycle is for 0.1319 years, out of which the inventory cycle is 1137 and the shortage portion is 0181. Now we substitute to get the total cost. Total cost is 4548.59 when we substitute for D, C0, Q, S, CC, CS. From all these we get 4548.59. Now when we compare this with the total cost in the first example, the total cost in the first example was 4898.98. The economic order quantity increases, the maximum inventory held in this system reduces, and the total cost reduces if we build back order into the same system. When compared to the previous model, we observe that the order quantity has increased, but the maximum inventory has reduced. Maximum inventory decreases in this. There is a gain in the order cost. That is because the order quantity has increased, number of orders per year reduces, therefore total annual order cost reduces. There is a gain in the carrying cost because the maximum inventory in the system reduces, therefore the average inventory in the system also reduces. The period for which we hold the inventory also reduces in this because there is a back order cycle or a back order portion. So there is a gain in the total annual carrying cost, but there is an additional back order cost which was not there in the first example. Now there is a gain in the order cost, there is a gain in the carrying cost, but there is an additional expenditure in the back order cost. So the net will be a decrease in the total cost. There is a net decrease in the total cost that we have seen. In the first model it was 4898.98, now it has come down to 4548.59. This also does not include the cost of the item. So there is a net decrease in the total cost, and this model would suggest that back ordering is always advantageous because the total cost comes down. Now we also observe, if we go back to this, now Q star is equal to root of 2D C0 by Cc into CS, Cc plus Cs by Cs. Now when shortage cost is set to infinity, the order quantities are the same. We can go back and substitute. This can be written as 1 plus Cc by Cs. So when Cs is infinity, Cc by Cs becomes 0. So the Q star becomes the same Q star of the first example. So only when the shortage cost becomes infinity, both the models become equal. Now we also observe that if Cs is infinity, the order quantities are the same. For all other values of Cs, however large a value we may give, the second model would yield a less total cost than the first and would always suggest that back ordering is advantageous. Now what is the learning from this model? The learning from this model is that we should keep Cs to infinity if we do not want back ordering and eliminate back ordering. The idea should be to eliminate back ordering by fixing Cs to infinity rather than encourage it by a wrong value of Cs. One should not exploit the fact that the total cost is minimum in this example, and therefore one should not be carried away by the fact that back ordering is advantageous. Back ordering has other aspects which may not have been adequately reflected in the Cs that is being chosen here. For example, it is very difficult to incorporate the loss of goodwill and loss of customer in this value. So even though back order by plan reduces the total cost, one has to be very cautious about the extent of back order that we allow when we accept back order as part of plan. So we need to keep the back order quantity minimum, and in order to do that we need to set the CS as large as we can. So, the issue is not evaluating the quantity S by defining CS, but the issue is keeping the CS large enough so that the quantity back ordered small s becomes small and manageable. So, it is necessary that shortages in practice should happen only due to uncertainty in demand, and if however if we want to plan back order at the planning stage of the inventory, then we need to keep a very large value of CS. The value of CS should be large enough to have a very small quantity back ordered. So, these are the things that we learned when we compare the first and the second models in inventory. Now, let us look at a third model where we look at something called a production consumption model. Now, in this model we assume an item that is produced in the factory and it is consumed either by assembly or by directly giving it to the customer. In both the previous models we were looking at items that were bought out. We were looking at items that were supplied by vendors and order was placed for these items. Now, we are looking at what happens in the production system. So, we are assuming that these items are being produced. Now, what do we do here? Now, we assume that the system is capable of producing at the rate of P per year, capital P per year. Production rate is P per year, which is greater than the demand, which is higher than, not equal to, higher than the annual demand. Now, because P is greater than D, we do not produce all the time, we produce only for a certain period. So, this is the period for which at which we produce, this is the period we produce. So, when we produce we also consume. So, for this cycle T1 the item is produced as well as consumed. It is produced at the rate of P, consumed at the rate of D. So, inventory is built up at the rate of P minus D. After a period T1 production stops and the item is only consumed from the inventory that we have built up. So, from this maximum inventory for the period T2 the inventory is consumed and the inventory becomes 0. We may assume that the production facility is producing some other item during this period T2. Now, once the stock position becomes 0, then we start producing the first item or the item under consideration, and then we both produce as well as consume. So, the inventory is rising at the rate of P minus D here, once again it is consumed and so on. Now, what is shown here is the rate at which it is produced. This is the production rate P at which it is produced. So, at every cycle of production we actually produce for a period T1 and only consume for a period T2, it is called consumption phase. The period T1 is a production and consumption phase. The total that we have produced is P into T1 because we produce at the rate of P for a period T1. So, total production Q is P into T1 and we consume, the maximum inventory that we build is P minus D into T1. So, in this model we have production rate is P per year, P greater than D, production is for a period T1, item is consumed for a period T2 and the cycle time is T1 plus T2. Now, in this model we need to look at a couple of things. Now, this Q is called the economic batch quantity. It is not an ordering quantity, it is a batch, it is a production batch quantity because we are looking at items that are produced in house. But if we use the same notation Q for the economic batch quantity for production. We also realize now in this case there is not going to be an ordering cost because we are not ordering any item here from the vendors. Instead of the ordering cost we have another cost called setup cost. So, every time the facility produces this item there is a cost incurred, just as every time we placed an order we had an order cost, every time we set up this facility for producing we have the setup cost. Now, setup cost we use the same notation C naught to represent setup cost in this model. So, annual demand is D, production rate is P per year, setup cost is C naught rupees per setup, which is similar to the order cost, but it is a different notation. C naught represent setup cost, carrying cost is Cc, order there is not order quantity here, the batch production quantity is Q, and maximum inventory in a cycle is Im. So, number of batches produced per year is D by Q, which is similar to the number of orders, but it is the number of batches produced per year which is D by Q. The annual setup cost is D by Q in D C naught by Q, because we have D by Q setups in a year, each setup is going to take C naught, so it is D C naught by Q. Average inventory in the system is Im by 2. Now that comes from this. Now total inventory is the area of the triangle, half into base into height, half into Im into T1 plus T2. Average inventory is total inventory by time, half into Im into T1 plus T2 divided by T1 plus T2, which would give us Im by 2. So average inventory will be Im by 2, and the inventory carrying cost will be Im by 2 into Cc. So total cost, which is the sum of the setup costs and inventory carrying costs, will be D by Q into C naught plus Im into Cc by 2. So in this model we are optimizing the total setup cost plus carrying cost. There is also going to be a carrying cost of inventory, because inventory is built up from 0 to Im and then subsequently consumed. So again this inventory that is built up and consumed results in items that are going to be there in the shop which have to be carried. So there is an inventory carrying or holding cost in this model. Now there is no ordering cost, but there is a setup cost, because every time we set up or want to produce this item we incur a setup cost. So here we optimize the total cost, which is given by the sum of the setup costs and the inventory holding costs. So total cost is D by Q into C naught plus Im into Cc by 2. Now the variable is Q and not Im, so we have to write this Im in terms of Q. To do that, we have Q equal to P into T1, Im is equal to P minus D into T1. This comes because from this figure we realize that for a period T1 we produce. Every time we set up, we produce for a period T1, produce at the rate of P. So P into T1 is the quantity that is produced, which is the production quantity Q. So Q is P into T1, that is shown here. Q is P into T1. Now what is the inventory buildup? Now as we produce during this period T1, we produce at the rate of P, we consume at the rate of D. So the inventory is built up at the rate of P minus D. So inventory is built up at the rate of P minus D for a period T1. So total inventory that is built up is P minus D into T1, which is Im. So Im is P minus D into T1. Now dividing one by the other, we get Im equal to Q into 1 minus D by P, or Q into P minus D by P, which is Q into 1 minus D by P. So substituting, we would have total cost Tc, we go back and substitute for Im is equal to Q into 1 minus D by P. So we substituting, we get total cost is equal to D by Q into C naught plus Q into 1 minus D by P into Cc by 2. Now we want to find out the best value of Q that minimizes this Tc. The value of Q that minimizes the total cost is obtained by setting first derivative with respect to Q to 0, differentiating with respect to Q and setting it to 0, we get minus D by Q square C naught plus Cc by 2 into 1 minus D by P equal to 0, from which Q star is equal to root of 2D C naught by Cc into 1 minus D by P. Now if we look at this equation carefully, it is very similar to the first model, except that we have an additional term 1 minus D by P. We also realize something common. We have seen 3 models and there seems to be some relationship. The first model also had root of 2D C naught by Cc. The second model had root of 2D C naught by Cc into Cc plus Cs by Cs. The third model has root of 2D C naught by Cc into 1 minus d by p. So, the term root of 2 d C naught by C c keeps coming again and again. So, for the third model we have q star equal to root of 2 d C naught by C c into 1 minus d by p. Now, we consider an example to illustrate this. Let us look at the same data as in example 1, demand 10,000 per year. Instead of order cost, C naught is the setup cost, is considered to be 300 per setup. The inventory carrying cost is rupees 4 per unit per year, and the production rate P is 20,000 units per year. P is greater than D, D is 10,000 per year, P and D are expressed in the same unit, which is units per year. So, q star is root of 2 d C naught by C c into 1 minus d by p, 2 into 10,000 into 300, C naught is 300, it is assumed to be the setup cost per setup, very similar to the ordering cost, rupees per setup 300, C c is the same 4 into 1 minus d by p, 4 into 1 minus half, which is half. This gives us 1732.05 units. The maximum inventory is q into 1 minus d by p, on substitution gives us 866.03. T1 production cycle is 0.08666 years and consumption cycle is also 0.08666 years. Total cost is d by q C naught plus q into 1 minus d by p C c by 2, which is 3464.10. Now, let us extend this model to backordering. Just as model 2 was an extension of model 1 considering backordering, model 4 is an extension of model 3 considering backordering. So, very similar, except that we introduce backordering. So, we introduce a CS, which is the shortage cost or the backorder cost, and the inventory figure looks like this. Now, we start with inventory equal to 0, produce at the rate of P and consume at the rate of D. So, inventory is built up at the rate of P minus D. We build a maximum of IM, which is equal to P minus D into T1. Now, once that inventory IM is built up, we stop the production. We assume that the facility is producing some other item during this period, and then we consume. Start consuming at the rate of D till the inventory reaches 0. We do not start the production immediately as we did in the previous case. We allow for some back ordering for a period T4, and we build a back order equal to S, and once the back order is built, we start producing again, and then we produce at the rate of P. Inventory increases at the rate of P minus D because we consume, and now it comes to 0, the back order is all met, and once again the cycle completes. So, now the cycle has 4 components, T1, T2, T3 and T4. T1 and T2 are the production components, T3 and T4 are the entire consumption component, but we have a T1 and a T2 because T1 production is all consumed and back orders are met. Now, T2 is consumed and inventory is built up. So, we have a lot of parameters in this model. We allow a back ordering and build a back order quantity of S, which is delivered or given as items are produced and inventory is built up, and then inventory becomes 0 after the back orders are given, and then the cycle begins. So, this figure adequately represents this model. So, let us derive. Now, we have 2 variables Q and S in this model. So, annual demand is D, production rate is P, setup cost is C naught, not ordering cost, setup cost is C naught, very similar to the ordering cost, carrying cost is CC, shortage cost or back order cost is CS, production batch quantity very similar to the order quantity is Q, back orders allowed is S, maximum inventory in the cycle is IM, number of setups in a year is D by Q, annual setup cost is D by Q into C naught. Because every time we produce Q, so number of setups in a year will be D by Q, so annual setup cost will be D by Q into C naught. Now, average inventory in the system is IM by 2, but held for a period T2 plus T3 out of a cycle time T. Now, we go back here. Now, there is a cycle time T, but the inventory but the total inventory of this quantity, that is half into Im into T2 plus T3 is held for a quantity big T or capital T. So, average inventory is Im by 2 into T2 plus T3 by T. So, Im into Cc by 2 into T2 plus T3 by T. Average backorder quantity is S by 2, but held for T1 plus T4 by T, once again can be seen from this example. Now, this is the total quantity backordered for T1 plus T4, but it is held for an entire period capital T. So, we go back and we substitute here to get this expression. So, total cost is D by Q into C naught plus Im by 2 into Cc T2 plus T3 by capital T plus S by 2 into Cs into T1 plus T4 by T. But we have only two variables that we are going to have, which are Q and S. Therefore, the rest of the things have to be written in terms of Q and S. Im, T2, T3 by T, T1, T4 by T, all have to be written in terms of Q and S. Now, let us do that. Now, Q is P into T1 plus T2. Now, Q is the quantity that we have produced. So, whenever we produce for a period T1 plus T2. So, Q is the total quantity produced or the batch quantity, which is P into T1 plus T2. Im is P minus D into T2, that is the inventory built up for a period T2 at the rate of P minus D, which is equal to P minus D into T2. It is also equal to D into T3. Similarly, S is the quantity built for back order, which is P minus D into T1, which is equal to D into T4. If we go back to this figure, we can understand this. Now, S is equal to D into T4, which is P minus D into T1. Now, capital T is the cycle T1 plus T2 plus T3 plus T4, and Q is D into T, because T is a cycle. So, we produce enough to meet the demand during the cycle. So, Q is D into T. So, substituting and simplifying, we get an expression like this. Im by Q is P minus D by P into T2 T1 plus T2. So, from which we have, and we use from similar triangles, T1 by T2 is equal to Im by S, which we can see here. We have this quantity is Im, this quantity is S. So, we go back, this is T1, this is T2. So, from similar triangles, Im by S is T2 by T1. So, we can go back and substitute. To first we get Im by Q dividing one by the other here, and then substituting from similar triangles, we get Im is equal to Q into 1 minus D by P minus S. This is an important equation which we need to substitute here for Im. And then we go back and we also get this T2 plus T3 by T is P into Im by Q into P minus D, or Im by Q into 1 minus D by P, and T1 plus T4 by T is S by Q into 1 minus D by P. We need these two terms, T2 plus T3 by T here and T1 plus T4 by T here. So, both are now written as Im by Q into 1 minus D by P and S by Q into 1 minus D by P. So, we have written everything in terms of the variables Q and S and the relevant parameters, which is here, and we have to substitute for Im square. We will get an Im square because there is an Im term here. T2 plus T3 by T also has an Im term. So, we get Im square. So, Q into 1 minus D by P minus S the whole square, and we also have an S square term, which is here. Now, we need to differentiate partially with respect to Q and S and set the first derivative equal to 0, substitute and get. And when we do that, we get S, the first equation we get on partially differentiating with respect to S would give us S is equal to QCC into 1 minus D by P by Cc plus Cs. Then we differentiate this expression with respect to Q partially, set it equal to 0 and substitute for S here. It is a very long, lengthy, involved derivation and substitution which we have not shown here. We have only shown the final result, and the final result will be Q star is equal to root of 2d C naught by Cc into Cc plus Cs by Cs into 1 minus d by P. Now this is a very interesting term because this Q star for the fourth model actually has all the terms that have appeared in models 1, 2 and 3. Now the first one was root of 2d C naught by Cc, root of 2d C naught by Cc. Second term was 2d C naught by Cc multiplied by Cc plus Cs by Cs. We have the term Cc plus Cs by Cs also coming here. The third term did not have Cc plus Cs by Cs but had 1 minus d by P. We also have that 1 minus d by P, and the fourth model has all the terms root of 2d C naught by Cc into Cc plus Cs by Cs into 1 minus d by P. Now let us consider an example to see or compare between models 3 and 4 because they are very similar. So we consider the same example with an additional data that Cs is rupees 25 per unit per year, the same Cs that we used in example 2. Now going back and substituting Q star, the economic batch production quantity is now found to be 1865.48. The quantity back ordered is 128.65 units, going back to the same equations. Now Im, the maximum inventory, will be Q into 1 minus d by P minus S, which is 804.09, and the total cost on substitution is 3216.338 or 334. Let us compare the corresponding values in the third example that we have seen. Now with the back order, economic order quantity is 1865.48. In the previous example, it turned out to be 1732.05. So we produce more per batch in the fourth one, which was expected. Maximum inventory is 866.03, which is actually lesser than what we have in the third model. The maximum inventory is 866.03. The fourth model, the maximum inventory is 804.09, which is lesser, which is understandable. We produce more but we hold less inventory because of the back orders that keep coming in. So maximum inventory held is less. Total cost is 3216. In the previous model, the total cost is expected to be higher. So in the previous model, total cost was 3464. In the model with back order, it is 3216. So very similar to the behavior that we saw between models 1 and 2, we see the same behavior between 3 and 4. Total production quantity increases, maximum inventory reduces, and the total cost comes down. There are three costs. Because the total production quantity is more, the number of setups reduces, so total setup cost reduces. Because the average inventory is less, the inventory holding cost reduces, but there is an additional back order which increases the cost of back ordering, but the net result is a decrease in total cost. So total cost comes down. So again we get an impression that back order provides us with a mechanism by which we can reduce the cost. We observe that the total cost comes down when back ordering is considered. Maximum inventory in the system comes down, though the order quantity is more, that is because of the back ordering that takes place. Now we would be tempted in this model once again to consider back order as favorable because the total cost comes down when we look at back order. We can again go back and show that only when Cs is equal to infinity, this model will become model 3, which is the third model, and there are two issues once again. For a given value of Cs, however large the value be, this will have a back order quantity S, and we will have a system wherein the total cost will come down. So the real issue is not to find out the S for a given value of Cs, but to define the Cs large enough so that the quantity S back ordered is small and it is manageable. It is preferred that back order is not assumed in the planning stage, because if we assume back order in the planning stage, we will get into a situation where it is favorable. So if we are however going to still assume back order, if we want back order by plan, the issue is to define the CS suitably high, so that the back order quantity S comes down and the system can be managed in practice. So, we have seen these 4 inventory models now, and we will look at inventory models with discount as well as multiple item inventory models in the next lecture.